Imagine falling into a black hole, not watching one through a telescope, not seeing an animation on a screen. I mean you falling in. You drift closer to the edge of the darkest object in the universe, a region of space so extreme that even light cannot escape its grip. The stars behind you stretch into strange arcs. The universe begins to distort. But something even stranger happens. Your watch keeps ticking. 1 second, 2 seconds, 3. From your perspective, nothing seems unusual about time at all. But far away, someone is watching you through a powerful telescope. Maybe a scientist orbiting safely outside the black hole's reach. And what they see makes absolutely no sense. To them, you begin to slow down. Your movements stretch out. Your falling body appears to crawl through space. Your heartbeat seems to fade. Your watch ticks slower and slower and slower, until eventually you appear completely frozen, suspended at the edge of the black hole forever. From their perspective, you never actually fall in. You just hang there, stuck in time. Here's the problem. From your perspective, you cross the edge of the black hole in a matter of seconds. From their perspective, you never cross it at all. Both observations are correct. Both are predicted by Einstein's theory of relativity. And both cannot possibly be true in the everyday way we think about time. So what is really happening? Does time stop near a black hole? Does it continue normally? Or does something even stranger happen to time itself? To answer that question, we have to confront one of the most uncomfortable ideas in all of physics. The idea that time is not what you think it is. Not a river flowing steadily forward. Not a universal clock ticking the same for everyone. Instead, time turns out to be something far stranger. Something that can stretch, bend, slow down, and possibly even end. And nowhere in the universe does this become more extreme than at the edge of a black hole. Before we talk about black holes, we have to deal with a much bigger problem, your intuition about time. Most people carry around a very simple picture of how time works. It feels obvious, it feels natural, it feels so self-evident that questioning it almost seems silly. Time, we think, is universal. One giant cosmic clock ticking away in the background of the universe, second after second, minute after minute. Whether you're standing on Earth, flying in an aeroplane, or drifting somewhere between the stars, that cosmic clock is supposed to tick at exactly the same rate for everyone. If two people both carry perfectly accurate watches, those watches should always agree. That's the intuition. And for most of human history, even physicists believed it. Isaac Newton imagined time exactly this way. In Newton's universe, time was absolute. It flowed forward steadily and independently of everything else. The planets moved through space, but time itself remained untouched, like a perfectly reliable metronome. But in the early 20th century, Einstein discovered something disturbing. That universal clock doesn't exist. Time does not pass at the same rate everywhere. In fact, time can stretch and shrink depending on two things: speed and gravity. Most people have heard about the first one. If you move extremely fast, close to the speed of light, time slows down for you compared to someone standing still. This is called time dilation, and it has been measured with astonishing precision using atomic clocks. But the second effect is the one that matters for black holes. Gravity also slows time down. And this isn't just a theoretical idea. We've measured it. Place one extremely precise clock on the surface of the Earth and another clock on a satellite high above the planet. The clock closer to Earth, the one deeper in the planet's gravitational field, ticks slightly slower. Not by much. The difference is tiny, but it's real. In fact, the GPS satellites orbiting Earth have to correct for this effect constantly. Their clocks run slightly faster than clocks on the ground because they experience weaker gravity. If engineers didn't correct for it, your GPS location would drift by kilometers every day. That's how certain physicists are about this. Gravity changes time. The stronger the gravity, the slower time moves. Now imagine something far more massive than Earth. Imagine a neutron star. Now imagine something even more extreme, a black hole. A black hole is the ultimate concentration of gravity, a mass so dense that it crushes space-time itself into an almost unimaginable curve. Near something like that, the effect on time doesn't just become noticeable, it becomes overwhelming. Clocks closer to the black hole tick slower, and slower, and slower, until eventually, right near the edge of the black hole, something astonishing happens. To an outside observer, time appears to almost stop. To understand what happens to time near a black hole, we have to talk about a very specific boundary, a boundary that physicists call the event horizon. The event horizon is not a physical surface. There's no wall there, no glowing ring, no cosmic barrier you can touch. Instead, it's a point of no return, a region in space-time where gravity becomes so strong that escape becomes impossible. Not even light, moving at the fastest speed the universe allows, can climb back out once it crosses this boundary. That alone would make black holes extraordinary, but the event horizon hides something even stranger. It's the place where time itself begins to behave in ways that completely defy our everyday experience. Imagine again that astronaut falling toward the black hole. At first, nothing looks particularly dramatic. They drift closer, pulled by gravity, just like any other falling object. Their rocket engines are silent. Their instruments are running normally. Their watch continues ticking away second by second. From their own perspective, everything feels ordinary. But far away, someone is watching. Perhaps a spacecraft safely orbiting at a great distance. Its crew aims a telescope toward the black hole and watches the astronaut fall. And something bizarre begins to happen. At first, the astronaut's motion simply slows down a little. Then it slows down more. The closer they approach the event horizon, the more their movement appears to stretch out. Their falling body seems to crawl through space. Their gestures become sluggish, almost like a slow-motion replay. Their watch, visible through the telescope, ticks slower and slower. Not because the watch is malfunctioning, but because time itself is slowing down near the black hole. As the astronaut approaches the event horizon, the slowing becomes extreme. Each second on their watch corresponds to more and more time passing for the distant observer. 10 seconds, a minute, an hour. From far away, it looks as though the astronaut is freezing in place. And then something even stranger happens. The light coming from the astronaut begins to change. The black hole's gravity stretches the light waves, pulling them toward longer and longer wavelengths. The bright signals from the astronaut's suit shift toward red, then infrared, then radio waves. Eventually, the signals fade into darkness. To the distant observer, the astronaut never actually crosses the event horizon. They simply slow down, fade, and disappear, frozen forever at the edge of the black hole. But this is only half of the story, because from the astronaut's own perspective, something completely different is happening. Now let's flip the situation around. Up until now, we've been watching the astronaut fall toward the black hole from far away. From that distant viewpoint, their motion slowed down, their watch ticked slower and slower, and they appeared to freeze at the event horizon. But what about the astronaut themselves? What do they experience? Surprisingly, from the astronaut's own perspective, almost nothing unusual happens at the edge of the black hole. Their watch ticks normally. Their heartbeat feels normal. Their thoughts continue second by second, exactly as they always have. If they glance back toward the distant stars, they might notice strange distortions caused by the intense gravity. Light from the surrounding universe bends dramatically around the black hole, warping the appearance of the sky. But the astronaut themselves does not feel time slowing down. To them, time feels perfectly ordinary. And when they reach the event horizon, the point where the outside universe believed they would freeze forever, They don't notice crossing any kind of barrier. There is no wall, no flash, no sudden stop. They simply keep falling. In fact, if the black hole is large enough, the astronaut might not even feel particularly strong tidal forces at the event horizon. Supermassive black holes, the kind that sit in the centers of galaxies, have horizons so enormous that the gravitational differences across a human body at that boundary can be surprisingly gentle. So the astronaut passes the event horizon without realizing it. From their point of view, the crossing happens in a finite amount of time, seconds, maybe minutes. But from the perspective of the outside universe, something very different is happening. To the distant observer, the astronaut never crosses the event horizon, ever. Even if the observer waits 1,000 years, 1,000,000 years, or longer than the lifetime of the galaxy, the astronaut still appears stuck just outside the black hole's edge, frozen in time. Both perspectives are valid. Both are predicted by Einstein's equations, and both cannot be reconciled using the ordinary idea that time flows the same for everyone. This is the core lesson of relativity. Time is not universal. There is no single clock governing the entire universe. Instead, every observer carries their own clock, their own timeline, their own version of how events unfold. The astronaut's timeline continues smoothly past the event horizon. The distant observer's timeline never shows the crossing happening at all. Two observers, two different realities, both correct. And this strange disagreement is not caused by faulty measurements or broken instruments. It is built directly into the structure of space-time itself. Near a black hole, the geometry of space-time becomes so distorted that different observers literally experience time in fundamentally different ways. To understand why that happens, we need to look deeper into what gravity actually is. At this point, it's tempting to think of gravity as a kind of invisible pulling force. The Earth pulls you down, the Sun pulls the planets, black holes pull everything. That picture works well enough for everyday life, but it's not what gravity really is. Einstein discovered that gravity is not a force in the usual sense. Instead, gravity is a distortion of space-time itself. To see what that means, imagine space-time as a kind of flexible fabric. Not a literal cloth, but a four-dimensional structure that combines space and time together into a single system. When nothing massive is present, space-time is relatively smooth. Objects move through it in straight paths. But when a massive object appears, a planet, a star, or something far denser, it changes the geometry around it. The mass bends space-time. The larger the mass, the deeper the curvature becomes. Planets orbit the Sun not because the Sun is pulling them with an invisible rope, but because the Sun has warped the space-time around it. The planets simply follow the natural paths through that curved geometry. Physicists call those natural paths geodesics. They are the straightest possible routes through curved space-time. Now here's the key point. Time is not separate from this geometry. Time is part of space-time. So when mass bends space-time, it bends time itself. Near a massive object, space-time becomes more curved and the paths through time stretch out. Clocks deeper in a gravitational field must tick more slowly compared to clocks farther away. You can think of it this way. Imagine two travellers walking across uneven terrain. One traveller walks across flat ground. The other must walk through deep valleys and steep hills. Both are moving forward step by step, but the traveller in rough terrain takes longer to reach the same destination. Gravity creates that kind of terrain in space-time. The stronger the gravity, the deeper the valley. And near a black hole, that valley becomes so steep that space-time itself begins to stretch dramatically. Clocks close to the black hole tick slower compared to clocks far away. Not because the clocks are broken, not because something is interfering with their mechanisms, but because the structure of space-time forces time itself to unfold differently. And nowhere does this stretching become more extreme than near the event horizon of a black hole. As you approach that boundary, space-time curves more and more sharply. To a distant observer, the stretching becomes so severe that the falling astronaut's clock appears to almost stop entirely. Time, from the outside perspective, is being pulled nearly to a halt. But the story becomes even stranger once the astronaut crosses the event horizon, because inside that boundary, space-time changes in a way that is almost impossible to visualize with ordinary intuition. Once the astronaut crosses the event horizon, the rules of the universe change in a very strange way. Outside the black hole, the astronauts still had choices. They could fire their rocket engines. They could try to slow their fall. They could attempt to move away from the black hole. Gravity made escape difficult, but not impossible. Inside the event horizon, that freedom disappears completely, because the geometry of space-time itself changes. To understand this, think about how we normally move through the world. At any moment, you can choose which direction to walk: forward, backward, left or right. But there is one direction you cannot choose. You cannot choose to move backward in time. No matter what you do, time carries you forward. Second by second, moment by moment, you move inevitably toward the future. Inside a black hole, something extraordinary happens. The direction toward the singularity, the center of the black hole, becomes as unavoidable as the future. Outside the black hole, moving toward the center is a direction in space. Inside the event horizon, that direction behaves like a direction in time. In other words, falling toward the singularity is no longer optional. It becomes part of your future. Just as you cannot stop tomorrow from arriving, you cannot stop yourself from moving toward the singularity once you're inside the horizon. You could fire rockets, you could try to steer away, but every possible path through space-time still leads inward. Every future moment lies closer to the center. Physicists sometimes describe this by saying that inside a black hole, space and time switch roles. Outside the horizon, time is the direction that carries you forward, while space allows you to move freely. Inside the horizon, the inward direction behaves like time. The singularity is not just a place waiting somewhere ahead, it is a moment waiting in your future. And just like the future, it cannot be avoided. This realization leads to one of the most unsettling conclusions in modern physics. If you cross the event horizon, your journey toward the singularity is no longer something that might happen. It is something that must happen. Every second that passes carries you closer to it. And eventually, the structure of space-time itself drives you to the very center of the black hole, a place where our current understanding of physics completely breaks down. Eventually, the astronaut reaches the final destination inside the black hole, the singularity. If the event horizon is the boundary of no return, the singularity is something even stranger. It is the point where space-time itself appears to break. According to Einstein's equations, all the mass that formed the black hole collapses into a region of extraordinary density. Space-time curves more and more as you approach the center, becoming steeper and steeper, until finally the mathematics explodes. Density becomes infinite, curvature becomes infinite, and our equations stop making sense. Physicists use the word singularity not because we fully understand what it is, but because it marks the place where our current theories fail. General relativity, the theory that describes gravity and black holes so beautifully, simply cannot describe what happens there. Something deeper must take over. Some new theory that merges gravity with quantum mechanics. But we do not yet know what that theory looks like. What we do know is this: for the astronaut falling inside the black hole, the singularity lies directly in their future. No matter what they do, every possible path through space-time leads there. And when they arrive, time itself may come to an end. Not because clocks stop ticking, but because the structure of space-time may no longer exist in any meaningful sense. Time, after all, is a way of ordering events, a way of saying, this happened before that. But if space-time collapses completely, if the geometry that defines distance and duration disappears, then the concept of before and after may no longer apply. In a very real sense, the astronaut's timeline could simply stop. Not fade away, not stretch forever, just end. Like the last frame of a movie with no frame that follows. This is one of the reasons black holes fascinate physicists so deeply. They are not just strange cosmic objects. They are laboratories where the known laws of physics collide with their own limits. At the center of a black hole, gravity becomes so extreme that our understanding of reality itself reaches a boundary. Beyond that boundary, we do not yet know what happens. Some theories suggest space-time might tear apart. Others propose that quantum effects could prevent the singularity entirely. There are ideas involving quantum gravity, bouncing universes, even connections to other regions of space-time. But for now, these remain possibilities, not answers. All we can say with confidence is this: if you fall into a black hole, the journey toward the singularity lies ahead of you in time. And somewhere along that path, the laws of physics as we know them reach their final limit. A place where time, space, and the structure of reality itself may cease to behave in any way we currently understand. At this point, it's easy to think this story is only about black holes, extreme objects, rare places in the universe, strange environments that most of us will never experience. But the real lesson here isn't about black holes. The real lesson is about time itself. Black holes don't create strange physics. They reveal it. Because the uncomfortable truth Einstein uncovered is this: time was never universal in the first place. We only believed it was. On Earth, gravity is relatively weak. The differences in time between different locations are so tiny that we don't notice them in everyday life. Our watches stay synchronized. Our clocks agree with each other. It feels as though time is flowing smoothly everywhere, but that feeling is an illusion created by our limited environment. In reality, every object in the universe carries its own version of time. A clock on Earth ticks slightly slower than a clock far out in space. A clock on a mountain ticks slightly faster than a clock at sea level. A clock on a fast-moving spacecraft ticks slower than one sitting on the ground. And near a black hole, the differences become so dramatic that they are impossible to ignore. Black holes simply exaggerate what was already true. Time is flexible. It stretches, it bends, it flows differently depending on where you are and how you move. And this leads to a profound shift in how we must think about the universe. There is no master clock ticking for the cosmos, no single timeline that everyone shares. Instead, the universe is made of events connected by the geometry of space-time. Every observer traces their own path through that geometry, carrying their own personal clock along the way. Physicists call this idea proper time. Your proper time is the time measured along your own journey through space-time. Someone else moving differently through gravity or space may experience a completely different passage of time. Two observers can disagree about how long something lasted. They can even disagree about the order of events, and yet both descriptions can still be correct. This is one of the deepest lessons of relativity. Reality is not built around a universal timeline. It is built around relationships between observers moving through space-time. Black holes simply push this principle to its extreme limit. Near their event horizons, space-time becomes so distorted that different observers' experiences of time diverge dramatically. One observer sees motion slow to a halt. Another experiences time flowing normally. Both are following the same laws of physics. Both are living through the same universe. But their journeys through space-time carve out completely different stories of time. And that realization changes something fundamental about how we think about reality. Because once you understand that time itself can bend, stretch, and warp, you begin to see that the universe is far stranger than the simple ticking clock we once imagined. Somewhere out there in the universe, right now, a black hole may be swallowing a star. From far away, astronomers might watch the event unfold through their telescopes. They would see the star spiral inward. They would see its light stretch and redden as the black hole's gravity distorts the fabric of space-time. And as the star approaches the edge, the event horizon, its motion would begin to slow, slower and slower and slower, until eventually the star would appear to freeze at the boundary, its final light fading into darkness. From the outside universe, the star never quite seems to fall in. It just lingers forever at the edge of the black hole, suspended at the brink of time. But from the star's own perspective, something entirely different is happening. The star continues falling. Its atoms race inward. Its matter plunges past the event horizon without any dramatic signal that a boundary has been crossed. And somewhere, deeper inside the black hole, its journey continues toward the singularity. Two observers, two different versions of reality, both perfectly consistent with the laws of physics, because the universe does not run on a single universal clock. Time is not absolute. It does not flow the same for everyone, everywhere. Instead, time is woven into the geometry of space-time itself. Mass bends it, motion stretches it, and near a black hole, the distortion becomes so extreme that time can nearly grind to a halt for one observer while continuing normally for another. What black holes reveal is something profound about the structure of reality. The universe is not built like a giant clock with gears turning in perfect synchrony. It is more like a vast landscape of space-time, and every object, every planet, every star, every person travels along its own path through that landscape, carrying its own clock, living its own version of time. Near a black hole, those paths diverge in the most dramatic way imaginable. One observer sees a fall that never finishes. Another experiences a journey that ends at the deepest limits of physics. Two stories, both true, because time itself is not fixed. It bends, it stretches, and in the presence of a black hole, it almost stops.